Think about it. Every single day, we create and share billions of images. Selfies, vacation photos, memes, you name it. Our digital world is just swimming in them. But have you ever actually stopped to wonder how all of that stuff fits onto our phones and flies across the internet so fast? Well, today, we're going to dive into the surprising science that makes our digital lives even possible.
You know, it's kind of hard to wrap your head around just how much data we're talking about. Every single high-resolution photo is this massive package of millions of individual data points. Trying to send just a few uncompressed photos would be like trying to email a dictionary. It just wouldn't work. Our entire digital world would pretty much grind to a halt.
So that brings us to the big question, right? How is this even possible? How can a little device that fits right in your pocket store a whole library of images when each one is made of millions of tiny data points? Well, the answer isn't magic. It's actually a really brilliant piece of engineering called data compression.
Okay, so at its heart, data compression is all about making files smaller. But, and this is the important part, it's not just about, deleting things randomly. The real genius is finding a smarter, much more efficient language to describe the exact same picture.
And this gets us to a really crucial distinction, the difference between information and data. See, the information is the picture itself, the mountains, the sunset, your dog. The data is just the raw code, all the ones and zeros used to store it. The job of compression is to keep all the information, but seriously cut down on the data needed to represent it.
So how in the world does it do that? Well, the big secret lies in finding and getting rid of something called redundancy. You can basically think of compression algorithms as these expert detectives, and their whole job is to hunt down wasted space inside your image files.
And this redundant data, well, that's the villain of our story. It's any part of the file that's either repeated over and over again or is just plain unnecessary. It's kind of the digital version of using 10 words to say something you could have easily said in 2. It's just fluff.
And we can actually measure how good of a job these detectives are doing. It's called the compression ratio. It's super simple. You just take the original file size and you divide it by the new compressed size. So a ratio of, say, 10:1 means the file is now 10 times smaller. The bigger that ratio, the better the detective work was.
Now, stop and think about what a 10-to-1 ratio really means for a second. It's not just that the file is 10 times smaller. What it's really telling you is that a staggering 90% of the data in the original file was effectively wasted space. It was just pure redundancy.
So where is all this digital junk hiding? Well, it turns out that digital images have 3 main ways they waste data, and compression algorithms are specifically designed to go after each one. Let's break them down.
First up is what's called coding redundancy. So imagine an image that only has a few different shades of gray. A standard format might use the same amount of data, let's say 8 bits, to describe every single pixel, no matter if that shade of gray shows up all the time or is super rare. That's basically like using a giant moving truck to deliver a single shoebox. It's just wildly inefficient. All right, next we've got spatial redundancy. This one's pretty intuitive. Pixels that are right next to each other are often really, really similar. Think about a photo of a clear blue sky. Instead of storing the exact color value for millions of nearly identical blue pixels, what if we could just say, hey, this whole area here is blue? That is a huge amount of repeated information we could potentially just get rid of. And finally, there's irrelevant information. This is all the data that represents details so incredibly subtle that our eyes can't even see them. Think microscopic changes in a solid block of color. I mean, if we can't even perceive it, why on earth are we wasting precious data to store it? Okay, so we've identified the enemy, redundancy, in 3 different forms. So now what? How do we fight back? Let's zoom in on that first one, coding redundancy, and see one of these data diet plans in action.
Okay, so take a look at this chart. Let's pretend we have an image with just 4 shades of gray. That probability column tells us how often each shade pops up. And what you'll notice right away is that one shade, the one with value 128, makes up almost half the entire image. Meanwhile, 255 barely shows up at all. That imbalance is exactly what we're going to exploit.
This right here, this is the secret sauce. The strategy is called variable length coding, and it's something so simple and intuitive it's brilliant. You give short, simple codes to the colors that appear all the time, and you save the longer, more complex codes for the colors that are rare. It's a simple idea, but with absolutely profound consequences. And here's what that actually looks like. On the left, you've got the old, inefficient way, a fixed code. Every single color gets the same clunky 8-bit description.
But over on the right, that's the smart code. Our most common shade of gray, it gets a tiny, efficient 1-bit code. The rarest shades get a longer 3-bit code. We're literally tailoring the description to fit the image's actual data.
And here is the aha moment. Here's the incredible result. When you average it all out across the entire image, you're no longer using 8 bits for every single pixel. Because that super common pixel uses such a short code, the average number of bits you need per pixel just plummets all the way down to 1.81.
I mean, that is a massive, massive saving. Just by using a smarter way to write the code, we've wiped out over 77% of the data from the original file. That data was pure coding redundancy, and now, poof, it's gone.
Now, keep in mind, that was just one technique to fight one type of redundancy. A real-world image compression system, like the thing that makes a JPEG file, is this sophisticated machine that attacks all 3 types of waste at the exact same time.
And this is basically the blueprint for how it all works. Every single time you save a photo, a piece of software called an encoder runs. It takes your big original image and squishes it down. Then, every time you open a photo, a decoder, which lives inside your web browser or your photo app, takes that compressed data and rebuilds the image so you can see it.
So let's peek inside that encoder. It's basically a 3-step assembly line for fighting waste. First, the mapper deals with that spatial redundancy. Remember, the big blocks of similar color. Then the quantizer gets rid of all the irrelevant information our eyes can't see anyway. And finally, the symbol coder uses those smart, variable length codes we just talked about to fix the coding redundancy. It is a systematic attack on all 3 fronts.
And this brings us to the final and maybe the most crucial trade-off. See that middle step, the quantizer? Well, you can actually choose to skip it. If you do that, you get what's called lossless compression, a perfect, bit-for-bit identical copy of your original photo. But if you want a really small file, you use the quantizer. This is the lossy step, where that so-called irrelevant information gets thrown away forever to save space. The final image isn't a perfect copy anymore, but it's much, much smaller. So the next time you save a JPEG or send a photo to a friend, just remember this choice is being made, right there, behind the scenes. Do you want a perfect, flawless copy that takes up more space, or do you want a much smaller file that looks identical to the naked eye, but has left some of its original data behind forever? It's the fundamental choice that pretty much shapes our entire visual digital world.